Important question of software engineering for RGPV exam part 5. Question 10. Explain in detail about the DFD and its levels. DFD, short for data flow diagram, is a graphical representation technique used to visualize the flow of data within a system. It provides a clear and concise representation of how data moves through various processes and data stores in a system. DFDs are commonly used in software engineering and systems analysis to understand, analyze, and document the information flow within a system. DFDs consist of different levels, each representing a different level of abstraction and detail. The four main levels of DFDs are: 1. Level 0 DFD, Context Diagram. The Level 0 DFD, also known as the context diagram, provides an overview of the entire system as a single process interacting with external entities. It represents the highest level of abstraction and shows the system boundaries, external entities, and major data flows between the system and its external entities. The Level 0 DFD does not go into the internal processes and focuses on the system's interactions with its environment. 2. Level 1 DFD, Main Process. The Level 1 DFD expands on the Level 0 DFD and decomposes the main process into more detailed subprocesses. It breaks down the main process into its major functional areas or modules, representing the system's main processes and their interconnections. The Level 1 DFD identifies the major data flows between the processes, external entities, and data stores. 3. Level 2 DFD, Subprocessors. The Level 2 DFD further decomposes the processes from Level 1 into more detailed subprocesses. It provides a more detailed view of the system's processes and their interactions. Level 2 DFDs help in understanding the internal workings of the system by breaking down processes into smaller components. The data flows and data stores are represented at a more granular level, providing a deeper understanding of the system's information flow. 4. Level N DFD, Detailed Processes. If needed, the DFD can be expanded to more levels, e.g., Level 3, Level 4, and so on, to represent increasingly detailed subprocesses. Each subsequent level provides a more detailed view of the system, breaking down processes into smaller components until the desired level of detail is reached. The purpose of using multiple levels in DFDs is to enable a hierarchical representation of the system's processes and data flows. It allows for a step-by-step decomposition of the system's functionality, providing a clear understanding of the system's structure and information flow at different levels of detail. Each level provides increasing granularity and helps stakeholders visualize the system from different perspectives, aiding in requirements analysis, system design, and communication among stakeholders. DFDs are powerful tools for understanding system requirements, identifying potential bottlenecks or inefficiencies in data flow, and designing or improving system architectures. They provide a visual representation that simplifies complex systems and facilitates effective communication and collaboration among stakeholders involved in the development and analysis of a system. Question 11. What are the elicitation techniques used in the software requirements? Software requirements elicitation techniques are methods used to gather, clarify, and understand the requirements of a software system. These techniques help in identifying, documenting, and prioritizing the needs and expectations of stakeholders. Here are some common elicitation techniques used in software requirements engineering. 1. Interviews. Interviews involve direct interaction with stakeholders, such as clients, users, and subject matter experts. It allows for in-depth discussions to gather information about their needs, expectations, and constraints related to the software system. 2. Questionnaires and surveys. Questionnaires and surveys are useful when dealing with a large number of stakeholders or geographically dispersed teams. They allow for standardized data collection by providing stakeholders with predefined questions or statements to gather their input. 3. Workshops and focus groups. Workshops and focus groups involve bringing together a group of stakeholders in a facilitated session. It promotes collaboration, encourages brainstorming, and allows for active participation in requirements gathering, validation, and prioritization. 4. Observation. Observing users or stakeholders in their actual work environment provides insights into their activities, workflows, and pain points. It helps in understanding the context of system usage and identifying specific requirements based on observed behaviors. 5. Document analysis. Analyzing existing documentation, such as business process documents, user manuals, or system specifications, helps in extracting relevant requirements and understanding the existing system or processes. 6. Prototyping. Building prototypes, either low fidelity or high fidelity, allows stakeholders to visualize and interact with the representation of the proposed software system. Feedback from using the prototype can help in refining and validating requirements. 7. Use cases and user stories. Use cases and user stories are techniques that focus on capturing the functional requirements of the system from the perspective of end users. They describe specific interactions, scenarios, or tasks that users perform with the system. 8. Brainstorming. Brainstorming sessions encourage stakeholders to generate and contribute ideas freely. It promotes creativity and helps uncover requirements that may not have been considered initially. 9. Ethnographic studies. Ethnographic studies involve immersing the analyst or researcher in the user's environment for an extended period. This technique helps in understanding the user's context, work practices, and requirements by observing and interacting with them. 10. Joint application development (JAD). JAD sessions involve collaborative workshops with stakeholders, including users, analysts, developers, and testers. The sessions focus on requirements gathering, analysis, and validation, with participants working together to achieve consensus on the requirements. It's important to note that different techniques may be suitable for different contexts and project environments. A combination of multiple elicitation techniques is often employed to gather a comprehensive set of requirements and ensure the needs of all stakeholders are considered. The selection of the appropriate elicitation technique depends on factors such as project size, complexity, stakeholder availability, and the nature of the software system being developed. Question 11. How object-oriented design is used in the development of the software? What are the different metrics used for it? Object-oriented design (OOD) is a software development approach that emphasizes the use of objects, classes, and their interactions to design and build software systems. It is based on the principles of encapsulation, inheritance, and polymorphism. Object-oriented design provides a structured and modular approach to software development, promoting reusability, maintainability, and flexibility. Here's how OOD is used in software development. 1. Object modeling. Object-oriented design starts with identifying the objects relevant to the problem domain. Objects represent real-world entities or concepts and encapsulate their attributes, data, and behaviors, methods. Object modeling techniques, such as class diagrams and object diagrams, are used to visualize and define the relationships between objects and their properties. 2. Class design. In OOD, classes serve as blueprints for creating objects. They define the structure, behavior, and relationships of objects of the same type. Class design involves defining classes, their attributes, methods, and associations with other classes. Inheritance is used to establish a hierarchical relationship between classes, enabling code reuse and promoting modularity. 3. Abstraction and encapsulation. OOD promotes the concept of abstraction, which involves identifying and representing essential characteristics of objects while hiding unnecessary details. Encapsulation ensures that the internal state and behavior of objects are hidden and can only be accessed through well-defined interfaces. This enhances information hiding and modularity, allowing for easier maintenance and modification of the system. 4. Polymorphism. Polymorphism allows objects of different classes to be treated as instances of a common superclass. It enables flexibility and extensibility by allowing methods to be overridden in subclasses and providing dynamic binding at runtime. Polymorphism facilitates code reuse, promotes flexibility, and supports the concept of programming to interfaces. Metrics used for object-oriented design. 1. Coupling. Coupling measures the interdependence between classes or modules. Low coupling indicates a higher level of independence and modularity, while high coupling can lead to tight dependencies and difficulties in maintenance and extensibility. 2. Cohesion. Cohesion measures the degree to which the elements within a class or module are related and contribute to a single purpose or responsibility. High cohesion indicates a well-focused and understandable class, while low cohesion may indicate a need for refactoring to improve clarity and maintainability. 3. Inheritance depth. Inheritance depth measures the number of levels in the inheritance hierarchy. Excessive inheritance depth can lead to complex class hierarchies, making the system harder to understand and maintain. 4. Cyclomatic complexity. Cyclomatic complexity is a measure of the complexity of a software system's control flow. It counts the number of independent paths through a program's source code, indicating the number of decision points and the complexity of the logic. 5. Reusability. Reusability measures the extent to which classes or components can be reused in different contexts or projects. Higher reusability indicates more modular and loosely coupled designs, leading to increased productivity and reduced development time. 6. Maintainability. Maintainability measures how easily a software system can be modified, enhanced, or repaired. It considers factors such as readability, modularity, documentation, and adherence to coding standards. These metrics help evaluate the quality and design characteristics of an object-oriented system. By analyzing these metrics, developers can identify potential design issues, make informed decisions, and improve the overall quality, maintainability, and extensibility of the software system.